Hey everybody, Dave Lindbergh in Hong Kong. Another episode THD Podcast. Today, Simon's with us in Japan, and we're going to talk about reading the frequency response curve. So this is kind of a fundamental tool that's used by everybody building audio devices. So we kind of want to know, what is a frequency response? Basically, if it is an input-output measurement function, so you're taking amplitude and phase, and you're getting a measurement of the output in terms of a frequency response. So kind of see it across the whole spectrum of what's audible, even beyond what's audible by human ears for some really fanatics out there. So let's just jump over to Simon, and we'll talk about what it is and what to look for in a frequency response curve. All right. Hey, Simon.
Yep, sounds good. Hey, Dave, where did you get that frequency response curve from that you just put up? Found that from somewhere?
That's actually from one of my clients, the VM Sound. That's the new 6mm that's not out yet. So
very cool, very cool. Yeah. All right. So one of the things is often people put these frequency response curves out, and what I notice is a lot of the time nobody actually knows how to read it. So they kind of look at this curve and say, okay, great, it's a squiggly line. So what? What does that actually mean? But what we can do is just go through and figure out some of the main information we can get out of a frequency response curve. So a lot of the time we say it's nice to get a single figure. You imagine you want to talk about, like, what's the temperature outside, and we can say it's 21, and we just get a number, and everybody can understand nicely that's high or low or whatever it might be. But with the frequency response, it's very hard to take the audio performance of a headphone and compress it down to a single number. So people might say it has a sensitivity of a certain amount. But really what you hear is related to that frequency response or that curve shape. So I'm going to take a look at some of these first of all, just to insert earbuds, a very simple unit. And what's good about these? Go ahead.
Just to give people some perspective, like I kind of mentioned that they go, well, I didn't say it, but 20 hertz to 20 kilohertz is normally what most of these machines are measuring. But most people,
yeah, that's right.
I think most people, they hear from about 16 hertz to maybe 12 kilohertz. I mean, that's all that's really functional in the human, or how does that kind of play in? So what we look at, and how does it compare to what people hear?
I would normally, if I play by myself, I reckon I can get up to about 15 kilohertz. At the bottom end, it's harder to say because it goes from something that you hear to something that you feel. So there's no clear transition to I can't hear it anymore, because you start feeling those vibrations.
Okay.
But the high frequency, yeah, you're right. But as a general rule, if you say 20 hertz to 20 kilohertz, you've covered it pretty well. Mm-hmm. So just like the curve that you just splashed up, this is going to be a fairly similar type of a thing. It's an insert earphone. And when we look at the curve, you may already know this, but we'll just cover the basics. You have frequency on the x-axis along the bottom, starting at low frequencies, going to the mid frequencies in the middle, and high frequencies on the right-hand side. And then the y-axis shows us the SPL level, or how loud it is. So what the curve is showing us is at any given frequency, what's the SPL output compared to basically the rest of the frequency curve. Okay. So we might say, well, let's have a look. Actually, the loudest of this insert earphone is right down here at about 40 hertz. It's in the low frequency. You might say, that's unbelievable. It can't be that. But that's a characteristic, actually, of a headphone. If you know something about loudspeakers, you have this characteristic of at the very low frequency, you roll off to 0, and then you have like an F0. You have a resonance frequency. It's flat from that point onwards. Headphones actually do the opposite of that, strangely enough, because it's inside a fixed chamber. And so from your F0 upwards, it's actually sloping down. And so this F0 basically is down very, very low. So it will slope down like that. So one of the first thing that we're going to look at, start with the easy stuff, is at the low frequency. Where's the highest point in the low frequency? And in this case, it's down at about 40 hertz. I'm going to grab something else quickly just to compare. So I'm just going to talk about the low frequency for the moment. So maybe you hear that. Actually, I'm just using a pink noise signal to test, right? So just pumping out that noise, and the pink noise actually has all frequencies at once.
Right.
Not exactly, but a little bit like that. So let me just get this seated nicely. We get it. One side is not. Oh, there we go. There we go. Okay, good. So now this one actually has the low frequency is not the highest point, so it's been tuned in a different way. And we could say, okay, so this one is not a bass heavy headphone. See, the low frequency is actually going quite flat, which would be a good thing if you like that style. But it's not. It doesn't have as strong a bass as the other set of headphones. I'll grab one more just to make another comparison of low frequency. I might actually change it from pink noise to something else, although in theory you can use any pretty much any signal to get a frequency response as long as you're covering all the frequencies. So this one's really similar to that previous one, right?
Yeah, it looks pretty close.
The whole curve is higher basically, but that characteristic where it's just going up and up and up to low frequencies is more or less the same. And again, yep, that's exactly a very similar characteristic to the one that you're looking at, because I guess these are all insert earphones that are quite well sealed. So yeah, very similar. This is actually not the VM sound drivers, but it's got quite a similar curve.
Mm-hmm. Yeah, a little bit of change at the high end where everything starts to change, like you say.
Yep. So I just wanted to cover that point anyway. We can look at this, and this low frequency range would say we're looking around the, I would usually say maybe 200 or 200 and down. What's the level of that compared to the rest of the frequency spectrum? So in these ones, it's always higher than the rest of the frequency spectrum. So that would make it bass heavy, relatively bass heavy. Whereas this other unit, this one's also pretty loud, whereas this other unit, whoever's that is, you might recognize it. Somebody made that. Whereas that one is bass light. See, the low frequency is sort of lower or equal to the mid-range and high frequency, so that would make it bass light. So that's what you look at. How does that low frequency around here compare to the level at the rest of the spectrum?
So as a developer, somebody wanting to have good bass, because everybody, especially in consumer audio, they're always more bass, more bass. So it has a lot to do with the mechanical seal of the earbud to achieve that goal.
Yeah, absolutely. So for these type of insert earphones, from a certain point of view, let's say in the theoretical basis, if you have a perfect seal, an absolutely perfect seal, you would have unlimited bass. You'd have very, very strong bass. So any tiny movement by that speaker diaphragm would just increase the pressure in your ear canal.
Right.
You never really get that because there's always some tiny amount of leakage at some point. Even if you have a very well sealed thing, you pump some air pressure into it, it slowly dissipates over time. And I'll go back to these ones. And so what I'll do just to demonstrate that, you give me 1 sec, and I'm going to grab a little pokey thing and break the seal so we just see what happens when we do that to the low frequency.
All right. Just have some interlude music while we wait for Simon to come back.
Okay, so I've just got a bit of a pokey bit. Actually turns out to be a piece of cable, but that'll do the job. And what I'm going to do is slide that down between the silicon and the air coupler just to break the seal, and we'll see what happens as I do that. So I've actually popped the seal there. Okay, good. And that low frequency is dropped down a little bit. And I'll make it worse and worse. And it will drop down more and more. So you see, as that leakage increases, the amount of bass just drops off. That's a basic phenomenon of this system.
Right.
So the better air seal you get, the more bass you will get, basically. And of course, if you have a larger driver, it would move less to give the same amount of bass. But from a certain point of view, the driver size doesn't matter too much. So you can get away with smaller drivers, like big old earbuds, something like this. Might have it might be a 15 millimeter diameter driver in it. Whereas these things are be only sort of like, I think that these might be 8 millimeters or maybe 7.
Yeah.
So it's almost half the size, but it doesn't really matter because you've got this sealed chamber. So you contain all of that energy. You don't lose your energy.
I think 5.8 millimeters is the most popular selling driver size for earbuds with, a lot of the in-ear brands like a Jaybird or somebody like that. So it can really this kind of speaks to the idea that, a brand looking to source earbuds, they could spend a bit more focus on just the tips and the nibs that come with their products rather than, wanting to invest in other areas perhaps. You think that's, of course it's a holistic solution, but it seems like the seal is so important that it kind of leads the way to get that good bass.
True, but it is a double-edged sword because if you have a perfect seal, it could get really uncomfortable.
Right.
So you actually have this pressure lock in your ear. And if you're walking, it's a real problem because with each step you get a thud as the thing just shakes a little bit, but there's no pressure release. So you have this total thing. So like these little Sonys here that actually came with a phone that I got many years ago. They've got a real classic frequency response bit like this one that we just saw. But they're actually 100% sealed, 100%. There is no leakage path on the front chamber. So if you're sitting down carefully listening to music, they sound fantastic. But if you're trying to walk around, it's impossible because there's this thudding with every step. Even if you move, rustle your head around, so it's quite uncomfortable. Generally, you always want to have at least introduce some intentional leakage path, just so you don't have that pressure lock.
It's almost like relaxing the waistband during this pandemic, but you also like if you put memory foam. A lot of people play with memory foam ear tips, and get a big one in there. And yes, it's sealed, but over the time that it expands and the memory foam comes back to its original shape, it can become extremely uncomfortable. So we can
True. So there was that. What did I want to mention just quickly? So there's your low frequency. You basically can dial it up and down as much as you like, but you have to make a decision how much seal do you want.
Right.
And so like I said, that's right. I'll just hold that one for comparison. Just jump back to this other unit that we were looking at. Even although it's got huge drivers compared to those other two models, it's also got quite a substantial leakage. Let's see if you can get a view of that.
Yeah, well, I can see the control leak as well. So
you can see that little dot, right?
Yeah, that's what the control leak, right? Or
exactly. It's only a tiny hole. It's only a tiny hole, and there's also a piece of filter paper on the inside covering it, so it's not completely open. It's sort of it's got a resistive paper on it basically, but that's enough just to set that bass level. So whoever designed this is intentionally. It's quite obvious looking at the curve. They've played around with that tuning to get it to be as flat as possible, and they've done it pretty well. Basically, they've got this set up nice. We do notice that the left and the right have different levels, so there's a bit of a channel imbalance there, which is not the best. That might be just due to that variation in the leakage. Like it's one piece of filter paper to the next. Especially if you're using the cotton paper type of thing, there can be quite a bit of variation. Yeah. So it's hard to control.
Yeah, so the natural fibers have some inconsistency to them, whereas an engineered mesh from somebody like a Satie or what's it called, the those guys from Switzerland, whatever they're called, that do the acoustic mesh. Those are all calibrated. Do you see people using those to get more precise over cottons? Is that a...
Yeah, very popular now, very popular. Plus, of course, the waterproofing thing. You know some guys doing waterproofing mesh?
Well, yeah.
Acoustic mesh, is that right?
Yeah, of course, Fabritech, which is one of my other clients,
Yeah.
they buy the raw material and they convert it, and so you get different pitches.
And that'll be a nylon base or something like that. It's not cotton, is it?
It's synthetic. Yeah, it's synthetic, and it's a polymer, so it's engineered, and the pitch is quite precise. Like you can buy 25 micrometer pitch holes, and they're uniform across the board, or you can buy even larger 90, 200 micron, depending on what kind of airflow you want, and which all relates to controlling the airflow for those holes or ports on your headphones.
Yep. So that would make a difference in this case for sure. So that's enough on a low frequency. You see, you can just lift this thing up and down depending on how you adjust that leakage and that tuning. And it doesn't matter too much about the driver size. Of course, big is better always. You just got more power at your disposal, but it can be done with a small driver. The one thing to point out there, though, is if a small driver, you'd need a lot less leakage to get the same level of bass. So a large diaphragm, you could have more leakage. So in principle, you could have a large diaphragm thing would be more comfortable. You could have a larger leakage, less pressure seal, but still get the same amount of bass loudness out of it.
Okay.
And now on these type of insert earphones, the mid-range, generally there's not a lot to talk about because it's very flat, all the way up to high frequencies. I'll just go back to this little Sony one because it has a really tidy response, and it's worth sort of just mentioning. I'll get rid of that hold curve. So from the low frequencies all the way through the mid frequencies, basically nothing happens. It's pretty much a straight line. We'll have a look at some big over-the-air headphones shortly and see that doesn't stay the same for over-the-air headphones. But of course, in these insert earphones, that total volume of that acoustic volume is so small that there's no that standing wave frequency. So you've got almost like an ideal pistonic system, essentially, right up to getting up to the high frequencies.
Okay.
Now then, and what is this? This is the interesting one. We've got a peak here, right? And you see the same thing on the plot that you showed a few minutes ago. Another insert earphone. This is not the driver. It's not the earphone exactly. It's a tube resonance for the ear canal. So in all cases, we measure with this. I'll get the sunny side. There we go. We actually have an ear canal simulator built in, which is basically a tube with a certain length, just like your ear canal. And a bit like if you were to, and tubes like this have a resonance. You know, like if you blow over the top of a bottle, you can get a tone or a bit of a sound coming out of it. You're getting a very similar effect. Now, it's not exactly the same, but it's the point is that it's this resonance of that tube. And so this is the exact frequency of that will vary depending on how much space you've got outside.
Right.
Like what's the length of that tube? It's a wavelength question. But for most insert earphones in a human ear, you'd be around the sort of 3 or 4 kilohertz range.
Okay.
So you have this one resonance peak, and you'll see that over and over and over again, especially for insert earphones, where that you've got that tube with a vibration at one end. So you've got a very clean tube resonance.
Right.
So that's a standing wave of that. And you say, well, should we, sorry, go ahead, Dave.
I was just going to say, and some people have different couplers. Is that somewhat to do with the measurement when they have a coupler on their test and measurement system? The length is to preference?
Yeah, so you could do different couplers and change that by changing the length of it. But generally, it's always around that point. So that's the average sort of human ear length.
Right. Okay.
So if you have a look at the plot that you've got there again.
Yeah, just a moment.
See if you can pick out the same peak on your plot. I think your one was a little bit obscured slightly.
Oh, hold on. Just give us a second. Load up here a bit. So
yeah, I've almost got a slightly double bump. That looks really familiar, that plot, because I've built up something with probably the same driver, which has a very similar characteristic.
you might have.
So you're at
you might have played with the 7mm.
2, 3. You've got sort of like a bumps of 3-ish, and then 4, 5, and then a 6 kind of thing.
Mm-hmm. And so are these the harmonics of that resonance you're talking about that we look at here? Is that what that is, or is it something different?
No, so the harmonics won't start until a very high, a much higher frequency.
Out there, okay.
So, yep. So I chose this Sony one because it doesn't have, like your one has a preliminary sort of a bump going on. This one doesn't. It's got that really clean single tube resonance. I just wanted to put that up to point that out so you see that. And you might say, well, should we EQ that out? Because that's awful, isn't it?
Right.
Well, not really, because that's your ears. Your brain already knows that sound.
Oh, so does your brain? Your brain obviously has some natural EQ to it, so to speak. Like there's certain frequencies that the human ear, like 1 to 4K or something like that, we're attenuated to hear that, because it's kind of like our natural response for other humans coming to beat us up. Talk to us is more common nowadays, but yeah, so.
Yeah, exactly like that. But depending on the length of the earbuds, that frequency would move around a little bit. So if you have nothing in your ears, there'll be a similar kind of a resonance, but you can't hear it because that's just the world that you know. There's no reference for a world without that kind of a frequency response. But when you put in insert earphones, you'd shift that frequency probably up in frequency a little bit, I think.
Okay.
So I don't know, when you first started listening to insert earphones, I remember noticing that there's an oddity to the sound. You get used to it really quickly, but and I think it's something to do with that shifting that natural resonance of your ear canal. So
I remember
there's a strangeness to it.
You can monkey with your ears to kind of tune like the EQ. Like this is going back to the late 80s for me. But those old Walkman headphones, and you could like flap your ear over and cover, and you get kind of different sound from just playing with your ear around the insert earbud or headphone at that time.
Yep, that's the one. So that's the dominant feature of the kind of I call it the mid-range. Still depends on how you want to classify it, but somewhere in between mid and high frequencies. Then you'll typically get a corresponding kind of an anti-resonance. Mm-hmm. So the resonance builds up as you move past that to a slightly higher frequency. The opposite effect starts to come into play, basically. Okay. So you get sort of peak dip thing. Okay, and then you would see the harmonics essentially of that right up here. What have we got? Something around the
that's
the higher frequency range. So that was that one. I just wanted to contrast it. Let me just store a comparison curve. I just wanted to contrast it with this other unit that's got a little bit more activity in the high frequency. I don't know exactly why that is, but we can have a look. And this one's loud too, possibly too loud. I'm still using pink noise. I could actually change that maybe to a chirp, but it doesn't matter.
Okay.
It's a bit loud actually for this thing because the sensitivity is really high. So I'll just back the level off slightly. It's fine. Here we go. So this one doesn't really have the same distinct kind of peak that we saw in the first one, right? It's been sort of blended out quite a bit, and so that'll be maybe a design feature that they've worked on to try and smother that peak a little bit. Now, if you like it or not, I can't say. You know what I mean? It comes down to personal taste at a level.
Right.
I tend to think that Sony, just with nothing much happening, sounds a bit cleaner.
Mm-hmm.
So this type of thing sounds maybe it sounds brighter for sure, right? There's more sort of area under the curve or more energy in that high frequency, but could be a little bit cluttered, I guess might be one way to put it. We'll just flip back and show the comparison again. I accidentally removed that the first time.
So this is just going back and doing it with the same peak noise level for the other set of earbuds.
Yeah, that's right. So actually the for a frequency response, the test level, like the voltage doesn't matter because it's always scaled to per unit volt. So they're all on the same basis. So this would be the SPL, actually, okay then. This is the SPL level if we were to use 1 volt of signal input. Now we're not, actually, we're using whatever it was, 100 millivolts, so something suitable for an earphone. Mm-hmm. But in order to compare everything on the same, regardless of what volume setting you're using, we scale it to per unit volt, it's called. So, it's up around 120 type of thing. Some people like to use, I think it is 179 millivolts, which is equals to 1 milliwatt for earphones. If you want to do that, you just minus 14 off the number. It's just scale it down to 179 millivolts. So I will just flip to another curve. We've got one where it's just comparing those shapes, called the curve shape only. So that will take out, that overlays the two just on 0 dB. You can see here that this unit has a lot more energy in that high frequency region.
So in this kind of chart, if somebody was benchmarking some headphones, they could actually, we can visually see a difference, and then they could take it around their golden ears and go, well, which one do you like? And it's kind of, it's not necessarily just the technical, but it's also that human element to selection that's involved. So is that an issue for that brand? Is that part of the sound of that brand, or is it something that...
Absolutely. Yeah, absolutely that. So, it makes it very easy. And also sometimes you'll have a sample and think it doesn't sound quite right, but the human ear is really good at fixing up the problems for you, doing a lot of error correcting. So sometimes it's hard to pick out what's going on, and you just want to be able to see the technical side of that curve, what's actually going on. So, I was just going to say that the previous one is it's got more energy, say, in that high frequency range. Specifically at what frequency, I don't mind too much. I'm sort of imagining going to use this analogy to say how bright sounding is it, how much high frequency is there. You can imagine that if you were to kind of take an average, or say on this Sony one, if this is a pile of dirt and you take some of the dirt off the top to fill in the hole until you get it all leveled out, what would the curve look like there? So your ear can kind of compensate for these things to a degree, okay, just in the impression of how loud it sounds at high frequency to you. So if I was to chop that dirt off and fill up the hole, I'd be pretty much flat, actually, just as a rough guesstimate. Whereas this other unit, this bullet thing, I'd actually be quite a bit higher, like there isn't really a hole there to fill in. Maybe right above 10K, I'd need to, stuff a bit of dirt down into that hole to fill it up.
Right.
It'll give you an idea that level is a bit higher, so it does sound brighter.
So then some people would be taking this information and then they, in perhaps the digital domain, adding EQ to maybe they selected their hardware, their drivers already, and they just want to touch it up in a final stage of production. So in Bluetooth especially, it's so much easier nowadays. Just a few biquads on your Bluetooth chip, and you can adjust these things almost.
Absolutely. Cool. All right, how are we going for time? Time for one more?
Sure, let's keep going.
Okay, I'm going to just take a look at an over-the-air headphone where things start to get really busy. Let's grab that. All right. Interlude music that you had ready.
Oh, I'm going to just mention to people, if there's any questions or something, please feel free to post down in the comments, and we'll be sure to hit you back with some answers. And if there's anything you'd like us to talk about or measure, or something cool related to headphones or audio in general, we're definitely hip to to talk about it and take a look at it if we know anything about it. We're not going to perpetrate that we know anything, but we like to chit chat about audio. So let us know, guys. All right, go ahead, Simon.
This good old classic MDR 1As, not a bad unit. It's that, you recognize that one?
Yeah.
It's quite popular just as a real basic but good performing over-the-ear headphone. Cabled only in this case. I haven't bothered with the Bluetooth stuff. We'll just use the cable for now. Matter of fact, what I will do is switch over to the chirp, just because I tend to get a bit of get better signal to noise ratio with a chirp as opposed to a pink noise. And I can put the voltage up a little bit too for a bigger headset, whatever. I don't have to be exact with that. With the insert earphones, you capture all that energy right into the microphone coupler. So you have quite a lot of inherent noise immunity. With an over-the-ear headphone, you don't have so much noise immunity because sound can pass through that housing quite easily. Okay. So doesn't that look nice and flat? Well, wait until we zoom in a little bit. So as I mentioned about the noise immunity type of thing, so the low frequency is wobbling around a little bit more. I'm talking and knocking the table and introducing vibrations and things like that. So you get some idea about how much that matters. So, for example, if I tap on the side of the headphone, it just goes berserk, right?
Right. So yeah, it wouldn't.
Okay. Anyway,
if you were measuring these things in a production quality control environment, you probably have a little chamber or isolation booth to put the headphones in and run the measurement.
You can put it into an isolation chamber.
Yeah, that helps keep one of those controlled variables, or helps add a control to the variables that might give you bad feedback or bad reporting.
Flipped over to Bluetooth for some reason, so I'm not hearing you.
Okay.
And now I have to figure out how to, I've got one idea. What I'll do is actually switch off the Bluetooth. 1 minute.
All right, and we're back.
Should be back now. Let's see.
Yeah, you're up.
Great. So, classic.
It's okay.
Somebody switched a Bluetooth device on and it paired automatically. Took over my phone.
Okay,
so
maybe a neighbor. I don't know. That sometimes can happen.
First of all, you can see that it's a lot more busy and wobbly. In the low frequency part, we've got the peak. Right there, it's at 90 hertz. Yeah, and then from 90 hertz, it's dropping off. So this actually has the lowest frequency is kind of 90 hertz. So you'll still hear the sound below that, but that's just how it's set up. And you might say, well, I'd like it to be, totally flat along there. Well, it can be done. Again, it's one of those leakage issues.
Right.
Just as it is for an earphone. So if you can create it.
Are there over-ear guys that play with different cup materials to try to play with the seal? Is that a thing like it is in insert ears?
So the cup material is not going to have as much of an influence as other things. So, for example, if you use wood or steel or plastic, you're going to get a similar effect.
So the cup.
Yeah, compared to the AirPad. So these headphones actually designed with quite a breathy, gentle AirPad. Mm-hmm. It's not one of those memory foam, quite heavy AirPads. And it's done on purpose just so it's lighter and airier,
comfortable.
And the consequence of that is that at a certain point, that low frequency energy will just dissipate out through the AirPad.
Okay.
A bit like, if you take it to one extreme, if you went all the way down to DC or to just pressure like a pump, if you just try to put some pressure onto there, that pressure will just escape really quickly. And the faster you move the pressure, you would start to go, you're going up in frequency, basically. At some point, you'd be able to hold that pressure, which will be around that 90 hertz point.
Okay.
And then just the same as we had with the earbuds, from that maximum point, basically, you just roll, you have a downward slope. Now, it's much steeper in this case. And so you go from that to F0, and then you head off downhill. Yep. And okay, now this is an interesting thing because you have a dip right here.
Yeah.
And that is, you'll see this in over-the-ear headphones, closed-back headphones. That's the tuning port of the rear side.
Okay.
In a speaker, you have a bass reflex port.
Yes.
So, and then you have this tuning frequency of the bass reflex port. The port on the back cup of a headphone is the same thing, but instead of, it's actually putting that energy to the outside world and is getting it from inside the ear cup, basically. So that's why you have the opposite effect.
Ah.
If you were to put a microphone inside a speaker box with a bass reflex port, you'd see where the bass reflex port is working, you'd actually get a dip coming out of the, not quite, okay, but it's pulling the energy off the driver and pumping it out to the back of the headphone. So the driver gets kind of stalled by that port, and therefore it has less output at that tuning frequency. Now, if you didn't have that port, your response would have a slope down like this.
Yeah.
Hands out of the way. And generally, you don't really want that. You want to be quite flat along the mid-range. So it's introduced on purpose to try and drop down from the low frequencies, get to a mid-range level where you can go evenly.
Okay. Now, is that port something you could monkey with on the fly so we could see it changing?
Yeah, let's do that. So I can. It's on the top here. I'll just show it.
Okay.
It's right there.
Yeah.
Yeah. So we can weed your finger in there and just block it. What I'll do first, we'll just get a clean curve. We'll store that. So it should be the left-hand side, which is the orange one. If I block that, by blocking it, what I do is I lower the tuning frequency. So I'm pushing it down in frequency. I can try and block it completely. Not easy to do because it's a large slot.
Mm-hmm. But again, in the design of this headphone, that would have all been selected, and then there might be some filter paper behind that port as well. So it's all kind of by design.
Yeah, exactly. So I let my finger off and it just goes back to its original tuning frequency. So as you make a port tube smaller, the tuning frequency, the diameter smaller, the tuning frequency goes down, goes lower.
Okay.
So this one actually, I think it doesn't have filter paper over the port. I mean, it has a little mesh so things don't fall in the hole, but it doesn't actually have a filter paper over the mesh. People have started to do that. It's been recent-ish, I guess, that people have been putting in 2 port tubes, one open and one with mesh over it. Okay. So you can do a bit more fancy stuff with the tuning. Okay, good. So that's the rear chamber porting effect. So if you made that port larger, you'd push this up in frequency. That notch would go up in frequency.
Okay.
But it will get to a point where it will stop having any effect, and that point is going to be somewhere around. I'm going to open this up so
yeah. Okay, we can see
we're bleeding off energy. So if I just turn it into a speaker, right? There's no more. I've removed the AirPad seal, and you can see now it's just operating like a speaker, basically. Mm-hmm. So that tuning frequency can't really go higher than that. It's a natural speaker frequency, basically. So you can operate in this range, and the lower end, you can't really go lower than that peak. So you have a sort of a limited range where you can move that notch frequency up and down before it stops having an effect because other things take over.
Okay.
for over-the-ear headphones, at some point we had that downward slope for the earbuds, right?
Yes.
When you've got a larger acoustic volume, at some point you hit a bottom where it stops sloping down and goes flat. And that's where it gets to the point where it's becoming like a speaker, because that volume compared to the frequency is largish.
Okay.
So it's like a speaker firing into, and that's the same point at which when I remove the earpad, you see it's this frequency around here.
Yeah, it doesn't really move.
It's where it starts going flat, basically, because it's just the volume in the ear cup is like a speaker type of thing. If I were to do the same thing, actually, just with an earbuds, I'll just put them next to, I'm not going to put the seal in, I'll just put it next to the coupler. And you'll see that the frequency point at which it is acting like a speaker, let's say, is right up here. It's really high.
Okay. It's almost like a
so when I make this
transition point in a sense.
Yeah, it is. Yeah, it is. So it's you call it a transition point. And so as with the speaker, below that resonant frequency, it just rolls off eventually to nothing. When I make the seal, from the low frequency would slope all the way down till it got to that frequency, but that's already right up at that ear canal resonance, so you can't see that effect anymore. So that's what's happening in the over-the-ear headphone.
Okay. You
go from the low frequency and you roll off, you slope down up until you get to that. I should come up with a better name than the frequency at which it looks like a speaker. But anyway, that's good enough for now.
We can give away a prize to somebody that comes up with a good name for us in the comments.
I should read some technical documents. Someone will have it figured out already.
Yeah.
Okay, then we start off into this region where we go into the resonances, and it gets real busy in a big headphone because you have larger distances and a lot of different distances. So you might have this, sound reflecting from one side of the ear cup to the other, longitudinally and one vertically, and then from the ear plate to the side of your head. There's all manner of possible paths where you can get these reflections and standing waves set up. Now, it's not that extreme, actually, because you can see there's a countable number of peaks in there. You might say 1, 2, 3, 4, 5, 6 or something like that. There is actually a countable number of resonances in there, and you could go through and figure them out by playing different games. So, for example, okay, let's see, we'll do one. If I reduce the distance between the side of the head, which is this headphone plate, and the driver plate, let's see if we can pick up which resonance shifts as a result of that distance, or which resonances shift. So squash the headphone in. Actually, none of them. Okay. The level goes up because I've just reduced that acoustic volume. So, the amount of diaphragm movement puts more pressure into that. Things like, if you have a great big container and you try to add a little bit of more air to it, no problem. If you have a tiny one, the pressure will go up. But actually, none of the resonances really moved. So what I just said about the reflection from the side of your head to the driver plate, I don't think that's happening.
Oh, but yeah.
Let's try another one. Let's try and squash the sides in on the earpad and see what happens.
I think the takeaway in terms of like the theme of like reading the response curve is you should not expect to have such a linear or flattish type of curve with the larger size of headphones. You have to be willing to understand that there's a lot of variables going on as you go bigger. And, it'd be kind of an amateur approach for somebody to say, oh, we want everything to be the same frequency response. Like if you're a purchasing dude at a brand, I go, yeah, we want our 40 millimeter drivers and over ear to be the same as a in ear. That's something that they shouldn't be asking for.
Yeah. So again, you can do that same trick just when you're reading a frequency response, where we actually started off with as a kind of a non-technical expert. Someone shows you the response, you want to get some information out of it. Yeah. You'd say in this case, okay, so my base here, I've got about 120 dB is that top point. So this is dB per volt input. It doesn't matter at that number itself, because I'm interested in how much does it differ from that low frequency to the mid-range. The mid-range there, I'm at 112. So I have 8 dB difference from mid-range to low frequency. So that might be a spec that someone has, like we like pounding bass, so we want 15 dB or 20 dB, gain, and call it gain at the low frequency compared to the mid-range. So it sounds very, very strong.
Mm-hmm.
And we'll also say that the bottoming out point is around 200-300 hertz.
Okay.
So I'm looking at it like this. I've got low frequency. Now I'm not worried. Okay, it rolls off fine. That you could increase the ceiling and sort of tilt that up to flat with a perfect seal, or that tilts down as you make it more airy and open.
Okay. So these are all the questions that people ask. Is it sealed back, open back? And then porting and all these variables go into producing this result.
Yeah, exactly. And so I'd look at what's the difference between mid-range and low frequency level. So is it strong bass? I mean, who's our other buddy? His one is the planar thing.
Oh,
his one is perfectly, yeah.
Yeah, shout out to True Analog.
Yeah. Okay. So his one is perfectly flat, basically, from mid-range and low frequency. And that's got an excellent sound, if that's what you like, you know what I mean? And that's very, very balanced type of an approach. But a lot of people like heavier bass. So, okay, fine. Can't argue with that. Then if we do our trick and we said, let's take some of this peak here and use it to fill in the holes, we would see, I've got an average, use this bit of thing. I've got an average, it's sort of sloping up a little bit like that. If I was to average through the mid and high frequency. So that sounds, that's what it is. It's got a certain character of sound like that. So, yep, it's enough to say that you can average out those peaks and dips in a first look.
Very cool.
To a certain extent, that a lot of these things will be fixed by other design decisions, like the ID, for example. What size? If you want a huge air pad and a big chamber, just because that's the style, then what they said, that speaker frequency is going to actually go down in frequency.
Yeah, or some of these gaming headphones, whether Turtle Beach or Razer, whatever, they'll have like some kind of, I don't know, like diamond design or something different, and that's your starting point to do the tuning, right?
Yeah, exactly. But if you really want to get, if you have a target that you want to go for, you need to have that in mind when you're doing the industrial design too, because certain things will be fixed into it, like the overall size that you've got in your front chamber. Yeah. It's just going to govern some of the mid-range characteristics. There's nothing you can do about it after that, or the size of the driver. So
I mean, so many of these things in audio, like the battle between industrial design and then acoustics is, who leads it. A lot of it's left up to, okay, here's the cavity you got to work with, and go fix it, acoustic engineer. I mean, that's a lot of what happens. So anyways, that's just the reality.
You do get that, but some of the A brands, they will have a platform that they evolve over time, and they know there's certain scope that you can change the cosmetics. So it doesn't look like it's necessarily the same thing, but inside they've got their dimensions worked out, the type of air pad that they like, and things like that. And so they just keep that same platform and maybe iterate on that slightly. They don't start with a clean sheet every time, just go to town. There's parameters that they're working to.
Okay, cool. All right, so we've almost done an hour here today, so maybe we'll table it.
Perfect.
Not to run on, but all right. Well, I guess thanks Simon for joining in from Japan, and anybody that likes this stuff, be sure to subscribe and please comment if you want us to talk about something that wasn't just BS. We do like to chit chat about audio ad nauseum. So Yeah. All right.
Yep, definitely that. Definitely that.
Okay. All right. Well,
Cheers, Dave.
again. Okay.
See you
Bye-bye,
later.
everybody.